Okay, we're going to go ahead and finish up chapter 10 here with 10.10, and we're going to do some applications of Taylor series here. And I know I've already been kind of talking about how good it is to use in a lot of situations here, but let's go ahead and see it done. So here we might reference back sometimes to our frequently used Taylor series table here, but just to kind of make the process a little faster instead of doing them all by hand. So let's take a look at this one. Let's express the integral of sine of x squared dx as a power series. So first, we're going to use our substitution method just so we'll be a little faster. And up above, if you look at the integral table, you'll find that sine of u would be u minus u cubed over 3 factorial plus u to the 5th over 5 factorial, so on and so forth. And so therefore the sine of x squared is, plug them in, x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial, so on and so forth. And then when we go to do this, we can actually do the integral then of this series. So integral of sine x squared dx is going to be basically the integral of that series. I'm just going to write it like this, right? This being the series, and we're going to get x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial, and so on and so forth. And then ultimately plus some c if we have something like that. So what we can do then is get that our integral is equal to c plus, plus some n equals 3 to infinity, and we'll have x to the n plus 4 over n plus 4, and then ultimately, whatever else's factorials are going in there. Okay, so there's that one. Now let's try actually estimating this. So it says estimate our 0 to 1 of x squared dx with an error of less than 10 to the negative 3. And so we're looking for 10 to the negative 3 is 0.001. So we're basically going to look until we get to that third decimal place type of accuracy, and then we'll basically stop there. So if we have our integral 0 to 1 of sine x squared dx, it's going to be x cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial, and we're going to evaluate this from 0 to 1. And when we do that, what we end up with is 1/3 minus 1 over 7 times 3 factorial, which is 7 times 6, plus 1 over 11 times 5 factorial. I'm not doing that one out. I'm not writing it out right this second. And so if we start looking at these, 1/3, about 0.3. This is about a 0.023. And then this one here I did, I did this one already, and it's going to be about 0.00076. So right there, we're past that third decimal place, and we don't really need to include anything after that, because from that point on, they just keep getting smaller and smaller. And so we can come up with essentially our answer being 1/3 minus 1 over 42, because that's the 7 times 6. And that'll give us about 0.3095. Now I had actually gotten it, and the actual one that Wolfram Alpha gives me for this when I went and looked it up is 0.31028. So we're pretty close. Now I know this one's a little off, but if it rounds, it'd be 0.31 for both of them. 0.31, and we're pretty close. We're getting over here to this third one. If you could include the next one if you wanted to make it a little more accurate, but that's probably pretty much good enough. I think it gives us an error of like 0.003 or 0.002 or something like that. So it's pretty close to a 10 to the negative third error. So let's take a look here at find a polynomial that will approximate the f of x, which is equal to this integral here, throughout the interval 0 to 1 with an error magnitude of less than 10 to the negative third. So again, we're looking for 3 decimal places there. We can do this by saying u equals negative t squared, and then we can get e to the u is equal to 1 plus u. Again, using that table up the front, I'm not working these out each time. Plus u to the third over 3 factorial, plus so on and so forth. And so our integral from 0 to x will become t, don't need an equal sign there, sorry, t squared times 1 minus t squared. I'm plugging this back in for you, right? Plugging this back in, that t squared minus t squared plus t to the 4th over 2 minus t to the 6th over 3 factorial, so on and so forth, and dt. And then we can do some distributing, and this will be integral 0 to x of t squared minus t to the 4th plus t to the 6th over 2 minus t to the 8th over 3 factorial plus so on and so forth, all dt. And then that's going to equal, when we actually integrate this, which is, you know, much simpler than the integral that's written at the top, this is just t cubed over 3 minus t to the 5th over 5 plus t to the 7th over 2 times 7 minus t to the 9th over 9 times 3 factorial, and so on and so forth. And we're going to evaluate this from 0 to x. And so when we evaluate it from 0 to x, we're going to get x cubed over 3, right? Those zeros are going to make each term 0, minus x to the 5th over 5 plus x to the 7th over 14 minus x to the 9th over 54, and then I'm going to even add some extra. It's going to be x to the 11th, adding some next ones on to 264, and then we'll have a minus x to the 13th over 1560, and then plus so on and so forth. And if you start looking at each one of these when we actually evaluate this, if we're doing it throughout the interval 0 to 1, one's going to be our biggest place where we're going to get the most error, and we need it to be accurate there. So we're going to look at x equals 1. And so when we do that, this one is going to become about 0.3, it's a third. This one's about 0.2, this one's about 0.07, this one turns out to be about 0.01, this one's 0.003, and then this one is 0.00064. So there we are, we're kind of past that third decimal. So really what we're interested in then to get us the accuracy, or at least right around the accuracy we want, is that part right there. So we're going to be interested in that part, okay? And that'll get us that kind of accuracy. So the next one, I am actually going to leave that one for you. If you just use the table above for natural log and do this, you can literally do this in like, what, 4 steps pretty quickly. And I'll write out what it is in the notes for you to look at, but try that one. You know, you're going to want to sub out for that natural log there. And then do the same thing that I did before. So let's take a look now at this. How about indeterminate forms of integrals, or limits, sorry. This one is going to actually equal 0 over 0. Now, you could try doing, you know, Hopital and all that stuff, but let's take a look at what happens if we actually use the series. So we have the limit as x goes to 0 of, and I'll put this in blue, sine of x, right? And then we're going to minus the tangent of x, and we're going to divide by x cubed. And then this is going to equal our limit as x goes to 0, and then we're going to just put in those series. So in blue I did sine, which was just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, dot, dot, dot. And then in red, I'll do this one, tangent of x is x plus x to the 3rd over 3 factorial. Wait, no, not 3 factorial, just 3. Plus 2x to the 5th over 16 plus dot, 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 so on and so forth. And this is all divided by x to the 3rd. And so if we start combining term by term, first you see that this x would cancel with that, and then you can combine this x to the 3rd here, negative x to the 3rd minus this x to the 3rd over 3. And when you do that, what you will get is limit x goes to 0. You combine those two, and you're going to end up with negative x cubed over 3, because this is x cubed over 6, this is x cubed over 3, so this becomes x cubed over 6, negative x cubed over 6 minus 2x cubed over 6, which is negative 3x cubed over 6, which is x cubed over 2, and I wrote a 3, over 2. And then you can combine the next one, the x to the 5th term, and you're going to get x to the 5th over 8, and then, so on and so forth, all divided by x cubed, which will give us the limit as x goes to 0 of negative 1/2. We're going to cancel out our x cubes here. That'll become a 2 and everything. Minus x squared over 8, minus so on and so forth. And then we have this in a form where we can actually take this limit. Every term is going to drop off to 0 because they're all going to have x's in the numerator, except for this one, which is just negative 1/2. And there you go. We got that one. The next one, if you look at this one, you could do Hopital, and you could get the limit as x goes to 1 by doing the derivative of the top and the bottom. So this would be 1 over x over 1, which is just 1. Or you can actually do the power series. All right, so this was Hopital. I don't know how to spell it. We'll just put Hopital. And then we can do a power series instead, Taylor series, whatever it is. And we can do the limit as x goes to 1. And then we can actually grab this. So we're wanting to look at this as x goes to 1. So what we're going to want to do is go back over here, and we're going to look at our natural log, one, and we're going to want to look at, we're going to actually not do at one, but I'm saying we're going to actually want the natural log of x, and so that means that we have to let like x, or like u equal 1 plus x, and you'll end up getting x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. So just do some substitution there, and that next one was going to be a minus. And, get this worked out, and you should be pretty good there. So I'm going to come back over here, and where was I? Oh, I was right there. And so we'll go ahead and use that here. So again, we just used that table up there, and we're going to get limit of x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus so on and so forth. And all of this is going to be over x minus 1. And so then we can go ahead and cancel it. So this was the series on top. And so we can go ahead and cancel this out. Cancel, cancel, cancel. Make that a 2 and so on and so forth. And we'll get the limit as x goes to 1 of 1 minus x minus 1 over 2 plus x minus 1 squared over 3 minus so on and so forth. And so everything's going to become 0 because 1 minus 1 is 0 and 1 minus 1 is 0. So these are all going to drop out, and we'll be left with just 1, which was the same answer that we got for the actual limit, doing it right above there. I'm going to skip that next one, and then I'm going to go on over to these. So let's take a look. at finding the sum of a series. So say we have this series, we want to know what it is. Well, what I'm going to notice is that basically everything has a 1 in it, and it's 1 plus 1 plus 1 on the numerator, 1 on the numerator, 1 on the numerator, and then we're getting the factorials in the denominator. So I'm thinking I'm going to let x be my 1 because we have that 1. Because we have a fixed 1 in each term. And so what I'm going to go ahead and do then is make this basically go back and look, and you can see that this actually fits very well with the e to the x then is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And if we go through and replace all these x's with 1s, we will get that series that we see right up there. So evidently, this series is simply e to the first. So that's just kind of looking for a pattern there that you can see and then figuring out which one it is. Let's try one more. And here we can say, if we look at this, you'll notice we have a 3/4 in every single one. 3/4 squared, 3/4 to the 4th, 3/4 to the 6th. So what I'm going to do is say that 3/4 is the thing that's fixed in each one of them, and I'm going to say x is 3/4. If that is the case, I go through and replace, and I'm going to get 1 minus, and then the 3/4 squared, so it's an x squared over 2 factorial, and then a plus, I'm going to have an x to the 4th over 4 factorial, minus so on and so forth, and it turns out that is just actually the cosine of x series, which means that this whole series is simply the cosine of 3/4. And I think that is it for this video. So hopefully that helps, and I'll see y'all later today.